Good morning, everybody. So, as it was said, it is our joint work with Grigory Kucherov that he is here, and our colleague from Israel, Dekil Tsur. It concerns approximate pattern matching, and there were already a few papers about this topic. Our goal is to construct a data structure for a given static test to perform search with mismatches under Hamming distance. This topic was widely studied before, and there are a lot of works concerning both cases of one mismatch and k mismatch in general case. But unfortunately, these data structures that are used, they usually occupy exponential in k amount of memory, or take exponential in value of k time for the search. Our motivation comes from fundamental problem in bioinformatics, that is read mapping, when you are given a huge text, a reference genome, and a large set of reads that are short strings, and you need to map these reads to the reference genome with mismatches. Our algorithm, our method is based on text indexing, so we need to construct a text index, and our implementation is based on a very popular FM index. But it's important that it can be extended, and it can be used with many other indexes. So the main property of FM index that we use is that it allows us to perform a backward search. Given all occurrences of a pattern in the text, we can compute occurrences of the pattern extended by one character to the left. You can ask why backward search, not, for example, forward search. It is easy to construct a structure from a structure for backward search to perform a forward search. But what's interesting is that there are special structures that allows you to change direction of the search during the search. So you can extend the pattern both to the left and to the right, then again to the left, then again to the right, and so on. And Lam and his colleagues in 2009 suggested such an structure, such an index called bidirectional FM index. Now I want to explain the most straightforward way how to use such a structure that is basically constructed for exact, for example, backward search to perform an approximate search. We can start with an empty string and then extend it character by character, both with the corresponding letters of the pattern and with all other letters from the alphabet. In this way, increasing the number of mismatches you have. So you should stop and return to the previous step if you obtain more than a low number of mismatches, or when there are no occurrences of the string in the text. So because it is unuseful to extend it anymore. And the complexity of such an algorithm can be measured in terms of number of visited strings. So during the search, you can obtain a search tree, and the complexity of this method can be measured in terms of its size. Lam and his colleagues suggested more effective algorithm for several cases of mismatches. So for one mismatch, instead of this straightforward one search, they used two independent searches. So they noticed that if you divide the pattern into two equal parts, then one of them will not contain mismatches at all. So you can you can do two independent searches. One of them starts with an exact matching of the first part, and in a forward way, in a forward direction, and then extended it by characters of the second part, allowing one mismatch. And the second search is backward search when you start with exact search of the second pattern and then extend it to the left in a backward way by characters of the first part, again allowing one mismatch. This can really improve the efficiency of the comparing to the this one search. Lam also suggested how to suggested a search scheme for two mismatch case. It consists of 3 searches. Forward search, that is, you start with exact matching of the first part and then continue to the right, allowing two mismatches, two accumulated mismatches. The second search is backward search. Then you start from the third part, allowing no mismatches. Then you continue with the second part, allowing one mismatch, or maybe 0, and then continue with the first part, allowing 2 accumulated mismatches. And the third search, it is the most interesting one because it uses the bidirectional property of the bidirectional FM index. We start with the exact matching of the second part, then continue to the right. We continue in a forward way, allowing one mismatch in the third part, and then we change direction and continue with matching of the first part, allowing 2 accumulated mismatches. So we use the bidirectional property here. I want to show how looks the enumeration tree for example, for the search. So we start with the exact matching of first part. It is 0, 1. Then we continue with P2, allowing 2 mismatches. Diagonal edges correspond to the places when we make mistakes, because we have the third character of the pattern to be 1, and this is a mismatch. We put 0 instead of 1. And then we extend the pattern with the string with the characters of P3, allowing 2 accumulated mismatch. So we will receive this tree. Of course, if in some vertex of this tree we obtain that there are no occurrences of the current string or the corresponding string, we shouldn't visit, for example, if we have no occurrences of the string 0, 1, 0, we shouldn't visit vertices of the subtree, because, of course, there will not be occurrences of the corresponding strings. In our work, we first suggested general definitions for a search scheme, how you can construct a search scheme for any number of mismatches, and how you can measure the efficiency of different search schemes. And secondly, we suggest 2 ideas how to construct an optimal search schemes and optimal partitions. Let's start with definitions. So, what you need to perform a search of a pattern. It is divided into into parts, and to perform a search, you need to know the order, in what you process the pattern, and then you need to know the lower bounds and upper bounds. For number of errors that you are allowed to do. So that 3 strings: the order, lower bounds for errors, and upper bounds. One such a search cannot cover all possible distributions of error between parts, so the search scheme is a collection of search that cover every distribution, every possible distribution of errors between parts. For example, the scheme that was suggested by Lam, the forward search performs search in order 1 to 3. Upper bound is 0 to 2, and lower bounds is 0, 0, 0. And the third search, bidirectional search, the order is 2, 3, 1, and upper bounds and lower bounds are here. Now, how we can measure the efficiency of the search scheme? Suppose that text and pattern are random, and we want to measure how many strings in average we will enumerate during this search scheme, during processing the pattern. We can write this equation for it, where AL is the number of enumerated strings of the given length, and estimate it with this expression, where and AL, value of AL can be computed using a recurrence relation, and it depends on the partition. So to construct an efficient and optimal search scheme, to construct an optimal partition, we suggest to do the several things. First is to use not equal parts but unequal sized parts. The second one is to use more than k+1 parts. So in the search scheme for two mismatches, Lam and his colleagues suggested a search scheme with 3 parts. We suggest to use more than 3 parts, for example, in this case. First, uneven partition. Why can it work? Let's look at that picture again, and we can notice that forward search allows you to do 2 mismatches in the second part, while backward search and bidirectional search allows you to do only 1 mismatch. So usually forward search will enumerate more strings, much more strings than bidirectional or backward searches. So increasing the length for the first part, we can decrease number of enumerated strings for the forward search dramatically, and hope that the number of total enumerated strings will decrease too. Now, what's about using more than k+1 parts? As we have noticed here, the forward search is the worst case because its upper bound, its U string is lexicographically maximal. So for a search scheme, we call a critical strings its maximal upper bound string. So, and of course, we want to construct a search scheme, to find a search scheme with minimal possible critical string. We proved theoretically that for k+1 parts, the critical strings, the minimal critical strings for search are these ones, for odd and even k. And for k+2 parts, it is here. So you can see that for k+2 parts, the minimal possible critical string is lexicographically smaller than for k+1 parts. And again, we can hope that it will, using k+2 parts, will improve the efficiency. A few words about computing. Optimal search scheme was computed just by a greedy algorithm, and for an optimal partition, you can use naive algorithm, just generating all possible partitions, and it will work for small values of k and small values of pattern length. But in our work, we used algorithm based on dynamic programming that works well for different values of k and pattern length, and it is faster. We did experiments. We used human chromosome 14 as a text, and its substrings, random substrings, as patterns, and searched these patterns in the text for 2 mismatches case and 3 mismatches case. Use different search schemes, equal sized parts, not equal sized, and k+2 parts, and compared them both in terms of number of enumerated strings and total running time. Here are tables presenting the results. So you can see that both our ideas can bring improvement for, and moreover, the running time and number of enumerated strings are in strong correlation between each other. So these were tables for 2 mismatches, and here are for 3 mismatches case. Just to outline, in our work we presented a general framework how to perform a bidirectional search with mismatches, and suggested 2 ideas how to construct an optimal schemes and optimal partitions. What can be done in the future? First, we can extend our method for edit distance. It is more complicated both in terms of theoretical estimations and experiments, but we hope that our algorithm, our method can be extended to this case. And the second thing is that we can try to construct search scheme and optimal partition simultaneously instead of consequent construction. And we hope that this can bring additional improvements. So thank you for your attention.
Thank you very much. Any questions?
Sorry, maybe I missed. Do you have any algorithm to choose an optimal scheme, which will give
Yes, we, as I said, we construct an optimal search scheme itself just by a greedy search.
And you can prove that it's optimal or not?
We can prove that its critical string is the minimal possible critical string.
And is there any relation between the critical string and the complexity of your search scheme?
We didn't measure it experimentally, but as I tried to explain you on the example of LAM scheme for 2 mismatches, the larger is the critical string, the more strings you will enumerate during your search.
Any other questions? Okay, so let's thank the speaker once again.